Direction cosines and ratios of a line passing through 2 points. Welcome, everyone. Let's begin our session by revisiting what we have already covered. In our previous lessons, we explored how direction cosines and direction ratios serve as essential tools to describe the specific orientation and tilt of a line within a three-dimensional space. Now, while knowing those values is incredibly useful, real-world geometry often presents us with a different challenge. We won't always be handed the angles or the ratios directly on a silver platter. More often than not, we will be presented with a scenario where we only know 2 distinct points that a line passes through. So, the focus of today's tutorial is to bridge that gap. I am going to show you the step-by-step method to derive both the direction ratios and the direction cosines using nothing more than the coordinates of those 2 points. By the end of this lesson, you'll be able to move from simple coordinates to a complete description of a line's direction. Understanding the concept. Now that we've established that direction cosines and ratios are tools used to describe how a line is oriented in space, let's look at the fundamental concept behind how we find them when we aren't given the angles directly. Suppose we are working within a 3-dimensional coordinate system and we are given 2 specific points. Let's call the first point P, with its coordinates defined as x sub 1, y sub 1, and z a subscript 1. Our second point is Q, with coordinates x sub 2, y sub 2, and z sub 2. If you imagine drawing a straight line connecting these 2 points, the line segment PQ can be thought of as a vector, a directed path that starts at point P and ends at point Q. To understand the direction of this line, we simply need to look at how much the position changes along each axis. Specifically, the direction is determined by the change in the x, the change in the y, and the change in the z coordinates as we move from our starting point, P, to our destination. Q. This concept of change is exactly what we will use in the next slide to calculate our direction ratios. Calculating direction ratios, doctors. Direction ratios are essentially the simplest way to represent the direction of a line. If you think back to our previous discussion on vectors, you'll realize that these ratios are actually just the components of the vector PQ$. In other words, they tell us how much the line moves in each dimension. To find these, we follow a very straightforward step-by-step process. First, we find the difference in the x$ coordinates by calculating x$ sub 2 minus x$ sub 1. Second, we find the difference in the y$ coordinates by calculating y$ sub 2 minus y$ sub 1. And third, we find the difference in the z$ coordinates by calculating z$ sub 2 minus z$ sub 1. Once you have these 3 values, you have your direction ratios for the line passing through P$ and Q$. We usually denote these using the letters $, B$, and C$, where $1 equals x$ sub 2 minus x$ sub 1, B$ equals y$ sub 2 minus y$ sub 1, and C$ equals z$ sub 2 minus z$ sub 1. Now, here is an important note to keep an eye on. Because direction ratios are proportional, the order of subtraction doesn't change the line itself. So, the set of x$ sub 1 minus x$ sub 2, $y$ sub 1 minus y$ sub 2, and z$ sub 1 minus z$ sub 2 is also a perfectly valid set of direction ratios. The only difference is that this set represents the direction of the line moving from Q$ back to P$ instead of P$ to Q$. Now that we have established that our line is defined by 2 points, P$ and Q$, let's discuss how we can actually represent its direction. Now that we have these ratios, in the next slide, we will learn how to use them to calculate the direction cosines. Calculating direction cosines, DCs. Now that we have successfully calculated our direction ratios in the previous slide, let's move on to the next step, finding the direction cosines. You can think of direction cosines as the normalized versions of the direction ratios we just found. In mathematics, normalizing simply means scaling our values so that they fit a specific standard. In this case, we want to scale our ratios so that the resulting vector has a magnitude of exactly 1. To achieve this, we need to divide each of our direction ratios by the total distance between our 2 points, P$ and Q$. Let's break this down into a clear, two-step process. Step 1, we need to calculate the distance between point P$ and point Q$, which we call PQ$. To do this, we use the standard distance formula in three-dimensional space. You'll take the difference in the x-coordinates, square it, add it to the square of the difference in the y-coordinates, and finally add the square of the difference in the z-coordinates. Once you have that sum, you take the square root of the entire expression. It looks like this. The square root of the quantity x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared plus z sub 2 minus z sub 1 squared. Step 2, once you have that distance, PQ$, we perform the normalization. We take each of our individual direction ratios, which we'll call $, B$, and C$, and divide them by the distance PQ$ we just calculated. This gives us our three direction cosines, which we traditionally denote as L$, M$, and N$. Specifically, L$ equals the quantity x sub 2 minus x sub 1, all divided by PQ$. Then, M$ equals the quantity y sub 2 minus y sub 1, all divided by PQ$. And finally, N$ equals the quantity z sub 2 minus z sub 1, all divided by PQ$. Once we have these values, we can see the direction of the line expressed in its most standardized form. In the next slide, I will show you a practical example involving a drone flight to demonstrate exactly how these formulas work in a real-world scenario. Illustrative example. Now that we have understood the theory behind calculating direction ratios and direction cosines, let's put everything we've learned into practice with an illustrative example. Imagine a real-world scenario. A drone is flying in a straight line from its starting charging station, which we'll call point P, located at coordinates x equals 1, y equals 2, and z equals -1. Its destination is a delivery location, point Q, at coordinates x equals 4, y equals 6, and z equals 11. Our goal is to determine the direction ratios and the direction cosines that describe this drone's flight path. Let's break this down into 4 clear steps. Step 1. First, we must clearly identify our coordinates from the given points. From point P, we have x1 equals 1, y1 equals 2, and z1 equals -1. From point Q, we have x2 equals 4, y2 equals 6, and z2 equals 11. Step 2, now we calculate the direction ratios or doctors by finding the difference between the coordinates, just as we discussed in the previous slide. For the x component, a equals x2 minus x1, which is 4 minus 1, giving us 3. For the y component, b equals y2 minus y1, which is 6 minus 2, giving us 4. And for the z component, c equals z2 minus z1. Be careful with the signs here. 11 minus -1 becomes 11 plus 1, which equals 12. So our direction ratios are 3, 4, and 12. Step 3, next we need the distance between point P and point Q, which we'll call PQ. To find this, we use the distance formula. We take the square root of the sum of the squares of our direction ratios. That is, the square root of 3 squared plus 4 squared plus 12 squared. Calculating the squares, we get the square root of 9 plus 16 plus 144. This simplifies to the square root of 169. And since the square root of 169 is 13, our distance PQ is exactly 13. Step 4. Finally, we calculate the direction cosines, or DCs. As we learned earlier, we find these by dividing each of our direction ratios by the total distance we just calculated. So L equals 3 divided by 13, M equals 4 divided by 13, and N equals 12 divided by 13. Therefore, our final direction cosines are 3/13, 4/13, and 12/13. As you can see, once you have the coordinates, it's just a matter of following the subtraction and division steps carefully. Key takeaways. All right, let's take a moment to recap everything we have covered in this tutorial so far to ensure the core concepts are clear. First, let's revisit the direction ratios, or doctors. As we saw when we were calculating the path of the drone in our example, the direction ratios are simply the differences between the corresponding coordinates of your 2 points. Specifically, you find them by calculating x sub 2 minus x sub 1, y sub 2 minus y sub 1, and z sub 2 minus z sub 1. Next, we have the direction cosines, or DCs. Think of these as the normalized version of the ratios. To get these, you take those direction ratios we just discussed and divide each one by the magnitude, which is the total distance of the line segment between the 2 points. This brings us to the fundamental relationship between the two. Direction cosine equals the direction ratio divided by the distance. It is a very helpful formula to keep in mind when you are moving between these two representations. Finally, there is a very important property called normalization. Because direction cosines represent the cosine of the angles the line makes with the axes, the sum of the squares of the direction cosines, that is, L squared plus M squared plus N squared, must always be equal to 1. Now, before we wrap up, I want to point out a few common pitfalls that students often encounter, so you can avoid them in your own calculations. Common mistakes. Now, before we conclude our session, I want to touch upon some common pitfalls that students often encounter when working with these calculations. Being aware of these will help you avoid losing marks on exams. First, let's talk about sign errors. This is perhaps the most frequent mistake. When you are calculating the differences for your direction ratios, you are subtracting coordinates. If one of your coordinates is already negative, you must be very careful with the double negative. For instance, as we saw in our drone example, if you have 11 minus negative 1, that must be treated as 11 plus 1, which gives you 12, not 10. Always double-check your signs during the subtraction step. Second, please be careful not to confuse your direction ratios with your direction cosines. I often see students perform the subtraction, find the direction ratios, and then stop right there, labeling them as direction cosines. Remember, direction ratios are just the differences, but direction cosines are the normalized values. A great way to check your work is to remember that because direction cosines are actual cosine values of angles, each individual value, L, M, and N, must fall between -1 and +1. If you see a number like 12, you know immediately that you are looking at a ratio, not a cosine. Finally, don't forget the square root. When you are calculating the distance, which we called PQ, you are summing the squares of the differences. It is very easy to get caught up in the arithmetic and forget that final, crucial step of taking the square root of that sum. If you forget the square root, your distance will be much too large and your direction cosines will be incorrect. Keep these 3 points in mind, and you will find much more success with 3D geometry problems.